Okay, so we'll continue from last time. Anybody here remember where did we stop last time? Anybody?
You gave us assignment.
Yep.
Ah.
Question.
Some topics.
Oh, really? What?
And also you want to explain more about the generation and the combination also.
Okay, what kind of homework did I give you?
Lattice constant, effects of semiconductor, and the differences between direct semiconductor material and indirect semiconductor material.
Okay, let's go for the direct and indirect band gap material first. Okay, anybody wants to start before I forget? The password for today's attendance is Haziq, give one.
Water.
Why water? Okay, water is the source of life. 90% or more of our body are from water and also the world. So, okay, water is the password for today. I give you 2 minutes to fill in. Fatin, after at the end of the class, can you wait? I would like to talk to you.
Okay.
Remind me at the end of the class.
Okay.
All right. So, finish? Fill in the form? Finish or not yet?
Yes, finish.
Okay. Good. So, okay, let's go for direct and indirect band gap material. Who wants to share first? Your findings. Huh?
Can I?
Yeah, sure. Also.
Differences between a direct band gap material and indirect band gap material is direct band gap is the minimum of the conduction band aligned directly with the maximum of valence band, and it has same value of momentum. For the indirect band gap material, it doesn't align it together, and the momentum change, the value of the momentum.
What do you mean by the value of the momentum change?
When of electron.
Yeah, the electrons. So when it happens recombination or generation, the momentum will when electrons go to each in other bands, it will go directly, but in indirect band gap material, it has to change because it's not aligned directly.
Okay, so your first statement before I ask the question, when you answer the question, you say the momentum change is actually not accurate. So you cannot answer just like that. You need to what happened the momentum change when what? Because it doesn't make sense when you say the momentum change, not doing anything, the momentum change. So you understand. So that's why this is a good example in the quiz or the exam. Sometimes you think you get the keyword. It's not only getting the keyword, it's actually explaining it. If you got the keyword right, but the explanation is not clear, you still don't get the marks. You still don't get the marks. That's a problem. So that's why take your time to explain clearly in the quiz or in the exam fully, so that everything people will I will understand what you meant. If it's halfway, I don't understand, I will not assume. I will not assume you understand. I will assume you don't understand. So you have to write until I understand. That's how it goes. Okay. Right. Good. So what's the importance of this direct and indirect band gap material?
Is to determine its conductivity.
Okay,
Kalau
interesting. Where do you get that? Kat mana? What's
dia macam determine the colors and conductivity of the material.
Conductivity? What does
dia pakai
conductivity means?
conductivity, I think it mean by the electron and holes conductivities for each type material.
So how does the direct or indirect band gap affect the conductivity?
Because the different in material, like for the
But it
material.
doesn't. But it, yes, but these we're talking about direct and indirect band gap.
Oh.
Kind of energy it releases.
Kind of energy. What do you mean?
When the recombination process occur in, for example, in direct band gap, it will release an energy in terms of photon. While in indirect, it will release, when it happens, the momentum, it will release energy in terms of a phonon.
Do you agree, Nasrin? Nasrin?
Because the direct band gap has high recombination compared to the indirect.
Again?
The direct band gap material has high recombination compared to the indirect.
Again?
Because the direct band gap material has high recombination rate compared to indirect.
So I was asking, do you agree with Osop or no?
Yeah.
You agree and you added that statement. Anizam, do you agree with Nasrin or not? Amirul, why are you late?
Sorry, madam, my class and read exactly at 3:30. I have face-to-face class just now, and I need to go back to the room. That's why it takes like 10 minutes to go back to the room.
Can you let who's the lecturer?
Madam Hashima.
Shima. Tell her that please I asked her to stop at 3:20.
Yeah. Before this, she always start at 3:20, but today he a bit late. He come a bit late. That's why he end a bit late.
Yeah, I don't care he comes late or come early, but she's taking my time.
Yeah.
Okay. All right. Apa tadi? Anizam, what do you think? What do you say?
I don't really understand the function of the direct and the indirect. So
You don't understand direct and indirect band gap material? Huh?
So I don't really, I can't really say I agree or I don't agree.
Do you do your homework?
Yes, but maybe not that deep. Because from what I know that the direct is when the minimum of the covalent band is aligned with the valence band.
Covalent?
Band.
Covalent?
Conduction band.
Covalent tu lain
line.
tom.
Conduction and
Balance.
Balance, bukan covalence. Okay, I know you still remember your SPM, you got an A in the physics, but covalent bond is something else. Okay, so don't miss between valence and covalence. Okay, covalence, valence, two different things. So you have no say. How about Fatin?
I have found the same thing as also and what Nasrin said, but I would like to add that about the energy that the also said. For indirect band gap, it is said that actually I also don't understand like, but I'm just explaining from what I read. So it is said that some part of the energy that it's emitted, it is transferred to the lattice, and the lattice will vibrate and generate heat. So basically, what I understand is that the direct and indirect band gap will determine the what do you call the properties of the semiconductor, because like for indirect band gap semiconductor, it is not suitable for light emission. For direct band gap semiconductor, usually used in laser and LED. So I feel like that is why it is important for us to know about that, so that we will know which semiconductor to be used in what.
Okay, so in answering the question, you agree with also, do you agree with Nasrin?
With Nasrin, I did read that it also said about the recombination process, but I do not really understand about that part. So I'm not sure um, about what Nasrin said. And it's not like I haven't found it. I did found it, but I decided to ignore it because I do not understand.
Is that?
Yes, madam. What I read in Google, the direct indirect is same with what Osop said before.
How about Nasrin?
I don't understand what Nasrin explained actually. But
Okay.
the momentum, what also our friend also said before, don't understand also about momentum.
Okay, actually, what Nasrin also was saying was correct, but what what Nasrin is saying is, I will argue whether it's right or wrong. Can you say your statement again, Nasrin?
The direct band gap semiconductor material has high probability for recombination compared to the indirect one.
High probability of recombination. It doesn't say what kind of recombination.
No.
Radiative recombination.
Okay, okay, all right. So I will now talk about this. Direct indirect is very important. Like, open my iPad. Let's draw this. Is the basis of one whole chapter on optoelectronics device. This is the basic of it. Semicon. Okay. Share screen. Alamak. Alamak. Kenapa? Unable to connect. Sebab tak ke Wi-Fi sana. Stop sharing. Stop sharing. Wait a second. Ni ada internet. Kenapa dia tak boleh? Itulah dulu tempat baru ni dia. Okay, while I'm trying to set this up, can you elaborate what is photon, what is phonon? What is photon, what is phonon? Come on, internet ni.
Photon is light. A light in terms of particles. Phonon is heat.
Is that correct, Adwa?
Correct, madam. But I also not so sure.
What are you not sure? Huh? Why are you not sure?
I not read it yet.
Amirul?
I think the same answer like the sister just now, but same. I also not sure what is the exact.
Hello? Can you hear me? Oh, okay, the internet downstairs. Okay.
Clearly.
Kejap. I think I need to change password for a while in order for me with my iPad. Okay, I want you to discuss among yourself. Photon, phonon, make sure you understand, and I want you to discuss about lattice, constant, and lattice. I give you like 5 minutes to discuss, and if you don't do your homework yet, do now. And if you know, if you don't know, you ask your friends here. Okay, I'll come back. I need to what do you call it? Change my password for this one. You can talk to each other.
Okay, madam.
Talking. Fatin, Gary, Fatin. Adik-adik kita lah sikit
Lattice.
Photon, phonon.
Betul lah tu, photon dengan phonon tu. Photon dia light particle. Kalau phonon ni heat macam heat dissipated. Phonon.
Biasa tak jumpa apa tu.
Itu dalam buku teks tu benda tu.
Oh ya, ulang balik apa?
Photon is the light particles. Kalau phonon macam heat dissipated. Is it right, Osop?
Yes.
But what Osop was saying is correct lah.
Yeah, Zik, can you elaborate more on that?
Medium record.
Like more, I need to know more on photon and phonon.
Photon form of energy dia dalam bentuk light kan. Photon dia maksudnya dia macam oscillation yang tak tahu betul ke tak, dia macam dalam lattice structure tu nanti. Dia lattice structure. Lepas tu bila photon tu kan dia dalam bentuk particle kan, photon ni. So dia emit lights. So I explain, aku rasa lagi forward. So I explain.
Also, can you help? Like, can you elaborate more on photon and phonon?
Actually, because light has two types of, like, it has two types, which is particles and waves. So I want to know what's the difference between these two. So I'm not sure, like, if I can elaborate more. So I'm sorry.
Okay. Can you see my iPad now?
Yes, yes. Okay.
Yes, madam.
Okay, great. Okay. Saya dah berlunjuk dah ni, lenguh dah kaki. So okay. Now, all right. Talking about photon and phonon. So what also was saying is right. So light, as mentioned before, you need to read on the wave duality. Go and read about this. Okay. Okay, just a note for myself. So so go and read about particle wave duality, where, as I mentioned before, light or anything particle or wave, it can behave both ways. It depends on the wavelength. Sometimes apa nama ni, the bigger we as a human being, our wave function is not as what do you call it, we as human being, this particle wave duality can occur in anything, including our body. Our body is particle, right? You can you can touch it, you can do whatever it is, but it can also behave like a wave. But because when the mass is big, the wave function is very a bit insignificant. But if something is very light, like a light, then it can something is very very not heavy, which is light, can also have a particle behavior. So the particle of because a light also have mass. Okay, light also have mass. It has mass. So when it has mass, it can behave like a particle. And when light behave like a particle, the name is photon. Photon. So what is phonon? Anybody?
Wave.
What do you mean by wave? Light also wave.
But when it behaves like a wave, it become heat. Oh no.
You people.
It's the opposite thing of photon.
No.
Let's try.
No, that's wrong. Okay. So photon is the particle of light. When the wave of light, we call it just wave light, you know. The opposite. So is when the light becomes a particle, we call it photon. But when it's in the wave, normally we already know light as a wave. Okay, normally we already know light as a wave. So when the light as behave like a wave, we still call it light. There's no other name. Phonon is something else. Phonon is the particle for heat. Okay, phonon is the particle for heat, and when the heat becomes a wave, we call it heat. You understand heat? Okay, heat is like it increases the temperature. That's heat. So okay, now I think my father dropped something in the kitchen. Something breaks. Okay, so now okay, let's talk about direct and indirect bandgap material. So okay, so this is a EK diagram. They call it EK diagram. You can read the textbook, right? There are many textbooks you can read. E is energy, K is momentum. So okay, energy versus momentum. The one that we draw, the energy band diagram that we draw, any. The y-axis is energy, right? but the x-axis is we don't give a dimension to it, but sometimes it can also be a distance, distance, but sometimes no, it doesn't really represent anything. Okay, the y-axis is energy. Okay, now, but x is some sort of dimension. But this EK diagram, so when we talk about band gap energy band diagram, the actual how it looks like, the energy band diagram, it doesn't look like this. It actually look like this. And in real life, when you do experiment, it is more complicated. It will be like that, and then like that, and then you know, they have many valleys. So life is not easy. So the electron hole, also the band gap also not is complicated. However, we as an engineer, we try to physics is also, we try to simplify things as simple as possible so that it's easy for us to understand. So that's why, although we have all this valley and a ripple of the energy versus momentum, we normally don't draw that. We just draw the big ones here. Okay, so let me remove this. It's okay. So this energy versus momentum. So so the electron will stay here. Free electron will stay here. Free hole will stay here. Okay, free hole, there are many free holes here. Okay, so but not to complicate things, we just draw one electron, one hole. Okay, now so where's the band gap? So the band gap is this one. The minimum, so the minimum energy for the upper electron to becomes free, right? So this is the band gap actually. Okay, so regardless of how you know, this normally we see it like this, right? When I ask you to draw the energy band diagram, it looks like this. Whether it's direct or indirect band gap material, you still draw it like this. Why? We have simplified it. It's supposed to look something like this, but we simplified it to be like this, so our life become easier. But you know, it's not that easy even, you know. But as complicated as it is, we try to make the explanation as simple as possible. So this one we translate to into become like this. So if we draw the energy band diagram like this, we don't know whether it's direct or indirect band gap material. So from this energy band diagram, you don't know which, if I put here the band gap is 1.41 eV. You just know, and then for example, and I put a Fermi level here. So from here, you can actually, you can find out what is the material. You can search 1.41 EV band gap for which material. As I mentioned, the band gap energy is the thumbprint. So if you know the band gap energy, you can go and find out, search for what is the material. So if you search, you will find this is actually gallium arsenide. Okay, and then from this diagram also, you know, it's a N-type gallium arsenide. Why? Because the Fermi level is close to the conduction band. But from this figure alone, you don't know whether gallium arsenide is a direct band gap material or not. Therefore, you need to go and search. So you can search gallium arsenide, is it direct or indirect band gap? Sometimes you have a table. They will give you a table of which materials are direct and which materials are indirect. So you better go and search now before the exam. Okay, so go and familiar yourself. I will not teach you how to search. So so if you look here, so I will remove. So this is the band gap of, we talk about band gap just now. So this is, we call this the direct band gap material. This is indirect. Why? Why we call that so? Because when you have recombination, it goes direct. Maybe I should draw it like this. There's no change in momentum because here, what's the x-axis? Is the momentum. So there's a direct recombination, and therefore there's no change of momentum. Therefore, the light is that you release the energy. Whenever I told you before, when recombination happens, it releases energy, right? It releases, it's losing energy. So this electron are losing energy from conduction band to the valence band. And how much is the energy lost? Is this amount, which is the band gap energy. Okay, and this light that comes out, so because this is direct band gap material, right? The energy that being released is in terms of photon, light. So for direct band gap material, you will only get light coming out if there's no defects. After this, we'll talk about defect. This we are talking about ideal case. Now, for indirect band gap material here, you can because this one I can draw it like this as well. So it means that still we can have recombination for indirect band gap material. Oh, why is it not moving? Oh, not moving, it's lagging. So so here, so this, if I draw like this, you can always have a recombination. So it means that indirect band gap material can also have recombination. But how does it recombine? It will go here and it will go there. So when this happens, it means there's a change in momentum from here to here, this amount of change of momentum. And whenever there's a change of momentum, since recombination, right? Recombination, you lose energy because electron from higher energy to a lower energy, it means that you will still have energy release. So this energy release is in terms of phonon, heat. It means that if you choose wrongly a material, you will not give out light. It cannot become LED, it cannot become laser, because when there's any recombination occurring, it can only give out heat. So it becomes warm, panas. So it increase the heat energy, the temperature of the semiconductor. So it's not that what we want. Okay. Any question up to here? Okay. Any question?
No question.
No question, madam.
Okay, so we talk about recombination. Okay, recombination is important. Normally, recombination is important for direct or indirect band gap material because there's a distinct whether it gives out light or heat, phonon or photon. Generation, both can have generation. Doesn't matter. Generation, when you have generation, you have free carriers. So both direct and indirect band gap material can give you generation, the same. Okay. Now, what I want to do now? Now let's talk about types of radiation. Okay, types of radiation. Okay. Okay, sometimes you got confused. Types of radiation. Okay. Okay. Sometimes I think I need to explain, otherwise you get confused. So when we have this what is this process called? The electron goes from the conduction band to the valence band. What is this process called?
Combination.
Recombination.
Recombination.
Good, recombination. Okay, so when you have recombination, it gives out a radiation, and this photon and phonon is also called radiation. It's energy released. Okay, so don't confuse this with nuclear radiation. But I think all of you don't care because you don't do research on that. But if you do masters or FIP that have nuclear radiation, you get confused. But now since you are not, that's okay. So you just understand, we can call this as radiation. Okay, radiation. So when you have recombination, you gives out radiation, and the radiation can be, and this photon, we call it radiative recombination. When something is giving out photon, the process is called radiative recombination. And then when something gives out phonon, this process of giving out phonon, we call it non-radiative recombination. It's just a name. Something that gives out phonon, we call it non-radiative recombination. It's just that the process that gives out, if it's called non-radiative recombination, you know it doesn't give out light. But if it's radiative recombination, you know it gives a photon. It's another name. It's telling you, you might read something and you think, oh, what is radiative recombination, non-radiative recombination? It's just the same. It's just the same, that it's just a process that gives out photon and the process that give out phonon. Okay, so now we know radiative and non-radiative recombination mostly. Okay, now we want to go to defects. Radiative recombination mostly are from band to band. Okay, band to band. So radiative recombination normally, what is it? I close it. Okay, normally we call it this radiative recombination. Mostly this process can happen through band to band radiation. We got band to band radiation, or we got band to band recombination. Oh, tak payahlah kita pakai recombination lah. Mix with what? Band to band recombination. What does this mean, band to band recombination? It means that you can see here, this is called, okay, this whole thing, brothers, this whole thing is actually conduction band. This whole thing is actually valence band. This is the same. So actually the conduction band and the valence band is not straight. It's not straight. It's not like how we draw it here. What we draw here is actually the tip of it. We only take this end and this end. We take about this end and this end. We simplify it. Okay, actually the conduction band has this shape. And valence band also have this shape, like a dome. Boleh? But when you draw, if you draw the energy band diagram in the quiz or exam, just use the simplified one here. If you want to draw like this, we go crazy lah, so difficult. Okay. Any question up to here? Are you sure? Kau saya tanya soalan boleh jawab tak ni?
Tak boleh jawab itu.
Dah, kenapa tak ada soalan?
Dia something baru jadi macam blur-blur sikit.
Tak boleh blur dalam kelas ni. Ada
Tengah proses tu hidup.
proses laju sikit boleh tak? Kena upgrade the processor. Okay. Alright. So if you don't have question in this class, make sure you have a question in next class. If you don't have question at all, you'll be in trouble because you won't that it shows that it will be difficult for you to understand if you don't ask question. I'm sure there's something you don't understand. Tanya je lah. Just ask question. Okay, so no question, I'll proceed. So you have this, so now I was talking about radiation. So you have radiative recombination, and you have non-radiative recombination. And radiative recombination mostly is band to band. Band to band means band to band. So from this to here, from conduction band to valence band. Okay, but if it's direct band gap material, band to band recombination will gives out photon. But for direct band gap material, you can have non-band to band recombination. It means that recombination doesn't go straight like this. How? Is when we introduce defects. Now I want to talk about defects. Before that, indirect band gap, non-radiative recombination here can also occur for band to band. This is band to band. This is also called band to band. But if it's indirect material, if even band to band recombination, you don't get photon, but you get phonon. Okay, so how to make it easy? So band to band recombination, which is radiative recombination, can only happen when it is direct band gap material. Other than direct band gap material, if you have band to band, it doesn't give out light. Okay. I don't know, maybe you're digesting, okay.
Madam,
Huh?
why does sometimes non-radiative radiation name is Shockley band hall?
Shockley read. All right. Shockley read.
Yeah, Shockley band hall.
Betul ke nama dia Shockley Band Hall? Awak baca kat mana? Bukan
Dalam-
Shockley Read Hall ke?
Saya baca Shockley band hall.
Awak baca buku mana? You sure?
Yeah, I think.
I don't know.
Later I check again.
Okay. Okay. Why is it called? I will explain now. Because it has to do with defects. Okay, now finish this. Radiative, in order for radiative recombination to occur, it must, the syarat, the condition that it must fulfill. Number one, it must be a direct band gap material. Number two, it must be band to band recombination. It doesn't fulfill these two criteria, it will not give out light. There's no photon. Okay, we want photon. So if you don't fulfill this, you don't get photon. So what do we get? We got non-radiative recombination. So for non-radiative, in order to get phonon out, okay, in order to get phonon out, there are a few ways that you can get non-radiative recombination. Okay, so I will write here again. Maybe black lah. I think that I'm angry at you. Okay. So non-radiative recombination can happen because of few things. It can happen. I'll put the short form. You remember the food B. Band to band can also, B2B is band to band, can also give non-radiative recombination if it is an indirect band gap material. So that's one way of getting a phonon heat when recombination occur. Number two is due to defects. I will explain more after this. And number three, you can get non-radiative recombination. What we call it, the process, we call it Auger recombination. When you have this kind type of Auger recombination, also you will get phonon. Okay, I will explain the three. So now let's go. You understand this already, right? Band to band, indirect, because it's indirect band gap material, it will give out phonon. Now let's look at defects. In order to understand the defects, we need to look at the lattice and lattice constant. Okay, this is the second thing I asked you. A few other things I asked you to find out, right? So after we talk about defects and this, after I talk defect, remind me to go back to this, and remind me at the end to talk about this, because I might skip it because I don't remember. Okay, so now so let's talk about defects now. Okay, now let's talk about defects. Did I ask you to find about defects?
Yes, madam.
Okay,
Yes.
what is the what are defects?
Defect could be the impurities or native defects or and extended defects.
What are defects?
The impurities,
Imperfection.
the dopant,
Imperfection.
impurities, imperfection.
Is there any difference between impurity and imperfection? Is it the
No.
same thing?
Yes.
Who said it's the same thing? Raise your hand now.
Yeah.
Who said impurities and
Impurity.
imperfection the same thing? Raise your hand. Only one? Only one? Ado, are you raising or no? Everybody has to answer, agree or disagree.
Different, madam.
Okay, the rest of you, so only Haziq and Adwa agree. The rest of you disagree. Okay, why you disagree? Amirul. Impurities and imperfection.
Then no. I'm not so sure, but the question is the other thing.
Apa?
It's not.
Allah teruknya internet.
I think it's another thing in
Another thing in semiconductor. Another thing. Okay, Izzat. Awak kat mana Amirul? Teruk benar internet.
itulah pelik je kan. Line penuh tapi macam lag.
Aduh.
Mobile buat hal.
Izzat?
Imperfection that occurs at a specific location or point. Impurities ni macam dopant yang madam cakap sebelum ni. Macam material. Imperfection macam sesuatu yang kita nak jadi kat location je. Or point in a crystal. Macam tu je saya faham.
Good. Do you agree with him, Anizam?
I agree.
Tiba-tiba pula agree. Why you agree suddenly, huh?
I just remember it is not it's the different thing. It's not the same. Because impurities is the dopant, what we dope into the semiconductor. Imperfection, it happened at the specific location. It's point defect in the semiconductor.
Yeah. So in the exam, you got that switch, you know, you get 0.
Yeah.
So be careful, everybody. I know it looks the same perfection. That's why I'm saying this course is very sensitive to terminology. This course is very sensitive to terminology because one terminology can mean something else, and then suddenly it's wrong lah if you use the wrong terminology. So sometimes you don't use the right terminology, also got wrong. So difficult lah. So try to remember the right terminology. So defects are, yes, anything imperfections in the lattice is called defects. Okay, any imperfection. Imperfection means is not ideal. Anything which is not ideal is imperfection. For example, okay, let's go a bit. Do you think Haziq, do you think you have imperfection in your face or no?
Yes.
Are you sure? Why you say yes?
Oh, I don't know. Maybe
Huh?
I don't know.
You understand my question? How about you, Adwa? Do you
I think because
huh?
it's not flawless like with
Like the
human.
model in the
Yeah,
Instagram?
yeah, yeah. Maybe like that.
Interesting. Interesting. So who? Let's deviate a bit. This I'm in my village, so let's deviate a bit. So I'm using that excuse. So who determines imperfections? Okay, so there's a standard that somebody put in order for to be perfect. This is the criteria: flawless, no pimple, six pack, slim and everything, right? That's the perfect. What the world is calling perfect. But interesting, in the Quran, Allah says, Allah had already mentioned in the Quran, Allah has already created humankind, the human, me, you, anybody as a human is already perfect in the eyes of Allah. So for us to call another human being or ourselves not perfect is wrong. Because Allah has, I can't remember, who knows that ayah? Something suar.
لقد خلقنا الإنسان في أحسن تقويم.
Yes. Thank you, brother, sister Osop. Panggil brother pula, sorry. Laqad khalaqnal insana fi ahsani taqwim. So Allah has created insan, human being, of the best of the mold. So nobody can say to another human being, he's ugly. Because if you say so, you go against what Allah says. And you say yourself is ugly or not handsome or not pretty or not beautiful, you're saying against what Allah says. So beautiful, but still many people still want to use the standard of the Instagram and all the magazine out there. So that's a problem. And then we feel low self-esteem for no reason. Then we go and buy branded things just to lift our self-esteem. Yes or no? When you wear Nike shoes, you feel like, oh, you're walking on the air. So you feel like you wear some jersey of the Manchester United original jersey, or you feel like, okay, I have confidence today. So there's something not right with how we view the world. Other than Allah says, we already are perfect in the eyes of Allah, how He created us. So we couldn't say our mold, whatever, how Allah created us is not perfect. Okay, now imperfections on the semiconductor. So ideally Allah created the atoms, the semiconductor, ideally perfect. That means that the lattice. What is lattice?
Regular arrangement of the atoms in the material.
Good. So if it's an ideal, if it's a material that is in the periodic table, which is ideal there, when Allah originally created it, it's ideal. It means the lattice. Let me draw again. The lattice. I hope you see the drawing of a lattice. What it is. I will draw. My drawing is not so good, but you can understand through my drawing. Lattice. Lattice is basically just arrangement, regular arrangement or arrays of the atom. So if an atom like this, so it has a pattern. And I'm drawing this 2D, two-dimensional. You can draw it 3D, but I'm not very good in drawing 3D. You can draw it 3D, and then, but let's just draw 2D because our capacity, we are not like artists, so we draw 2D. It's enough for us to understand. So lattice is this constant, this array of arrangements of atom. What is lattice constant?
Distance between two atoms in the lattice.
Okay, the distance between two atoms in a lattice is called lattice constant. And Normally we say it's A. The distance, the lattice constant is the space or the dimension between atom to atom, and different material have different lattice constant. Okay, some have a bigger lattice constant, some have a smaller lattice constant, right? That's how it is, how Allah created it. So it has different band gap, and also it has different lattice constant. Okay, now, so ideally, or this is an ideal lattice where it's regular, everything perfect, nice, beautiful. Okay, let's say one day, when you were, growing this semiconductor, I use the word grow. I cannot read my handwriting. Growing, we call the name some in silicon. Sometimes they use word fabricate. Fabricate can mean two things. Fabricate, it means in silicon industry in Malaysia. Sometimes they say fabricate. It can also mean grow. Means you start and then you put layer by layer the atom. Okay, and then the actual means of fabricate is after you get the layer, then you make it into mold. Okay, no, maybe I need to give an analogy. It's like growing is like, anybody here have done have helped their mother to make kuih lapis? Also, have you eaten kuih lapis?
No.
Yes, yes.
Huh? Have anybody here helped your mother to make kuih lapis? Any here? No?
Yeah, I have the experience.
Kuih lapis biasa beli
Siapa
je.
siapa
Kuih
I
lain buat.
Huh?
Kuih lapis biasa beli je. Kuih
Oh.
lain adalah buat.
Tapi nak kuih lapis lah, orang duk cerita kuih lapis ni. Ha.
Okay.
So, siapa pernah?
Yeah, me, madam.
Amirul. Oh, good. So your is it do you normally help, or is it just rarely?
No, it's not normal. I just how I need to try. Just put it above the previous one.
Each other, right? So maybe anybody can watch the process of making kuih lapis. Now we get all hungry together and we can go and find. I'm in the village, I can easily find this kuih lapis. So this is the kuih lapis also. So you can see here, can you see it layers by layers? And the process of making it is you need to put one layer and then put another layer and put another layer. And when you eat this kuih lapis, so you should go and eat kuih lapis after this, all of you. You can peel one by one. You can peel each layer. Okay, so it is made of coconut and tepung beras and flour, rice flour. Okay, so this is kuih lapis. So the process of growing semiconductor layer, they call it epitaxial layer. EPITAXIAL. Epitaxial layer. It means you grow layer by layer. Okay, that's how you can grow quantum well, quantum dot. You can grow very thin, layers of semiconductor. When you grow it, epitaxial layer, one row of atom, and then you put another row of atom. How you do it? We have like machine. We call it, there are many types of machine. We have MOVPE, molecular vapor phase something, MOVPE. You can Google it. And also we have MBE, molecular beam epitaxy. These are all expensive equipments, which where it's like millions to have it. We don't have it in IIUM. In any university in Malaysia, I don't think they have it. Maybe UM have it, but I don't know whether it's working or not, because it's so sensitive, and any break of the electricity, if there's a trip of electricity, the whole thing down, poof, and you lost millions of ringgit. So that's why in a country where the electricity is not stable, you better not buy, it's just waste of money. But in Malaysia, we have a quite consistent electricity, but sometimes it's also breakdown. When breakdown, that's it, millions lost. So when I was in doing my PhD in UK, they have this equipment, but I didn't use the equipment. I just characterize. So so what they do in the MBE, you can go and Google MOVP process. You can Google the video. They will show you they will put atoms in terms of gas on top of the layer. So for here, kuih lapis, we just pour, right? Pour. Amirul, right? You pour one layer and then let it set, put another layer, let it set. But in a MBE, they have gas. Okay, they have gas for if you want to make gallium arsenide semiconductor, they have gas of gallium and gas of arsenic. So, and in a very high pressure, like a vacuum chamber, they will release these two gas and we come together and it will bond and it will sit on the lapis, on the epitaxial layer, and we keep on growing. If you want it thicker, you put more gas. That's how it works. Okay, so when this process occurs, right, it's like cooking. So growing of semiconductor is like cooking. You need to have the right temperature. You need to know exactly how much atom you want to put. You want to put exactly how much pressure. If otherwise, right, if you cook, you change the temperature slightly, the cake will burn. Similar to semiconductor, there's also recipe, and the person who cook need to be really, skillful in order to make a very good semiconductor epitaxial layer. However, how good you are in this world, how good you are, you will never be perfect. Only Allah is perfect. Therefore, that's why in VLSI, if you ask the silicon purity, when you do this integrated chip, like the one in your handphone, in your computer, it's actually very, very pure. The silicon is very pure. You know how much is the purity? Purity means there's no impurities in, because when you add impurities in, it will gives out imperfection. When you add dopant, it actually make it imperfect. That's why we remember last time we have energy level inside the band gap. It's no longer ideal. So a pure silicon, the purity, I think you can Google. Nowadays it's like 99.99999%. That's how pure, because if it's not pure, even one dust it go inside the silicon, it will short circuit the whole entire circuit. And maybe it will, one diode broken, the whole circuit will not work. So where the defects comes from, this imperfection sometimes when you grow. When you have this kuih lapis, is your kuih lapis always nice, Amirul? Very nice like this in this picture?
Like the third picture.
This one?
Red, white, green, red, white, green, red, white.
This also you can see some imperfection. My kuih lapis, just to tell a story of kuih lapis, I tried to make my own kuih lapis when I was in UK, because my husband wants to eat it. So trying to be a good wife, I tried to make it. It took me the whole day, it's crazy just to make like this. And when it comes out, wow, with a lot of imperfections. So it doesn't come smooth like this. There are many bumps. My kuih lapis after one day waiting, ya Allah. Then after that, I never make kuih lapis ever again until now, which is fine. So and I respect those who do kuih lapis. Those, I don't know, I think maybe the temperature of my steamer was not right. I don't know what happened, but it's like I will not do it again. So imperfection due to the temperature or due to the mix, the recipe, the pressure, and the material that we put, sometimes will not give us a smooth smooth lattice. Okay, it will not give us the smooth lattice. Therefore, it can give us defects. And anything imperfection, another name of imperfection inside a lattice, we call it defects. Okay, and this defect can be in many ways. It can be defects in terms of missing an atom in the lattice. So for example, if I share the screen again, you can see my screen. Can you see? No? So if you see here, this is a perfect lattice, right? It can be imperfect if suddenly missing one atom here. No atom, it becomes defect. And this is called point defect. Because one point, there's no atom. It's called point defect. Okay. Okay, there are many types of defects. We can also lose an atom in a row like this. So if I lose like this, see, one row, there's no atom. And this, we call it the name dislocation. So it's not important for you to remember the name. We are not doing material engineering here, but enough for us to know that you can get defects inside the semiconductor by many ways. So there are many types of defect. You can, as mentioned, the point defect. You can have dislocation defects. You can have if you Google, there are many different kind of defects. So what does these defects do? If you look in the microscope, can you see the lattice? Yes, you can see the lattice inside a microscope. Why? Because the proton and neutron are heavy. It doesn't move. So what you see is you see is the reflection coming from the atom. So if you see in the microscope, can you see defects? Yes, you can also see defects. You can see the atom missing, or like this, you can see a row of atom missing. Okay, so you can see in microscope. So it means that this is the physical. If you look at it, physical, you can do experiment, you see physically with your eyes that atoms are missing. The question is, how does these defects affects the band gap? Okay, how does the defects in the end affects the band gap? The answer is, anybody knows? Anybody knows? Nobody?
Because the structure of the semiconductor is not ideal, so it will affect the conduction and valence band.
It will affect the conduction and valence band. How?
So if the effect on the conduction and valence band, thus it will affect the energy band gap.
Okay, answer it again in one sentence. How does the defect affects the energy band diagram?
Because the structure of the atom in the semiconductor is
Because
not
how? My question is how?
how. Jawapannya because. Bukan.
Tak. How is a process? Kenapa because pula?
Why? Because.
Okay.
How? Don't know lah.
Boleh tunggu. We don't know. Anybody else? You know it. Just put in a good sentence, Haziq. Another thing, I will also teach you English, everybody. So you get 3 in 1. You will get semiconductor, English, Islam. If you join my class, free Islam and English, I give it for free. Okay, right. So so how do we answer this? How does the defect affects the energy band diagram? Anybody?
Can I try?
Yeah, sure, Fatin.
I think the formation of defects, it requires energy, so that's why the never mind.
Okay, good try. Good try. I admire your imagination, but it's not right. So, any more?
Can I try, madam?
Yes. Who's that?
Anasri.
Anasri, go on.
When the concentration of holes and electron is different, so the energy band will be different from the ideal one. kalau sebabkan the missing atom. So
Yeah, missing atom, but it's just 1 out of 10 billion.
okay.
Will that like change the number of carriers, affecting the total number of carriers?
No.
Not really.
Yeah.
Okay, good imagination also as well. I admire your imagination, but can we, ada orang lain, anybody else want to try?
The effect dia punya
English.
Maybe it will affect its Fermi level. How? Because it's pushed toward the conduction band.
Not really. Okay, the answer is, brothers and sisters, remember I told you, right? Why in here? This is called gap, right? But this is called an energy band gap. This is called band gap, and sometimes called forbidden band gap, right? Forbidden band gap. Why? Because in here, ideally there shouldn't be any energy level, right? Shouldn't be, and you shouldn't have any energy level. When you add impurities, which is the dopant just now, you have energy level inside the band gap. When you have defects as well, it introduces energy level inside the band gap. When you have defects, it introduces, normally we say ET. T stands for trap. Trap energy level. Trap and defects the same thing. Sometimes we use defect, the name defect. Sometimes we use trap. Why trap? Because it traps carriers. Defects traps carriers. So normally we don't use ED because it becomes a donor ED, then we confuse with the donor atom. That's why we say we use the ET. Okay, so defects introduces energy level inside the band gap. Okay, so it can be in the middle here. It can be anywhere you want to be. It depends on the type of defect. It can be over here. It can be over here. It can be over here. So anywhere. It depends on the type of defects. So having defects in the physical structure over here, translates to energy level, trap energy level inside the band gap. Okay, now we understand that, right? So that's how it translates. It becomes a trap energy level. So next question is, how does this, what does this have to do with anything? Yeah. Answer my husband. Okay. So so what's the question? So how does these defects do anything? This energy level of defects. So now we go back to this. Remember here, non-radiative recombination through defects. So how does that affect? Now I'm answering this question after you understand what is defects and how does defect affect the energy band diagram. So if you have an electron here, right? This electron wants to recombine. So band to band recombination, it will go through like this. This is band to band. However, now, as I mentioned, whenever a carrier need to exist, it need to stay in the energy level. It cannot stay exist anywhere. So now the electron have an option. Instead of band to band, the electron have an option to go. And this we call it recombination through defects. See, the electron recombine through defects. So it will stay here for a while and then it will go there. Okay, recombination through defects. And this recombination through defects is okay. If this material here is a direct band gap material, let's say gallium arsenide, direct band gap material. if we have this direct bandgap material, recombination through defects, what comes out? So you can see, if you look here, there will be two energies coming out. This energy and this energy, right? Yes or no? This one is only one energy coming out. If it's direct, you get photon, light. But now, the electrons are recombining through defects. And what happens is, you will get two types of other, you have other two energy loss. And both are phonon. Whenever you have recombination through defect, it gives out phonon. And what is the energy of the phonon? Here, it depends on where the trap is. If the trap is here, so here it will go like this. If it trap over there, it will go like this. Okay. So it's like if you're going to jump, right? If you yourself going to jump through a river, you're going to jump the whole river, or there's a wood or boat inside the middle of the river. It's easier to jump to the boat and then jump to the other side, right? The same goes to a electron. When it wants to generate or recombine, here we talk about recombination, but the same thing, generation can also be through defects. So how? So it's the opposite. It goes through like this. So generation is the opposite way. So defects introduces energy level inside the band gap. In the end, it gives a route for the electron to stay. So, but the not good thing is, if you have defects, you have more of this non-radiative recombination. It means that your LED will not give as much light as you want, and many will give out as heat. And in the end, it will damage the LED. So we don't want defects inside any optoelectronic device. For generation also, we also don't want defects, because the problem with defects, you cannot control how many defects you want. Normally, it's a random process. These defects are random process. We like engineers, we like anything we can control. Anything we don't control, tiba-tiba surprises we don't like, because we cannot control the situation. Defects also like a surprise. Sometimes it can be a lot, sometimes it can be middle and little, and not only that, it can stay anywhere. So this trap, this defect, it has it introduces the trap energy level, and also it has, I will write it nicely. It also have big NT, and here is the number of concentration of the trap. NT here is the concentration of the trap. So you can have one trap or many trap of the same thing. So the more you have the defects, the higher probability that you will be recombining through the defects. Okay.
So the higher energy loss lah, madam. Kalau higher number of NT.
What do you mean by energy loss? For photon, if you need to be careful when you say, because photon also energy loss.
Just now madam said about the phonon for the electron. So more energy loss because it's jump around many times.
You need to be careful when saying energy loss, brother. I say energy loss is anything. Energy loss is from higher energy to lower energy. It can be photon or it can be phonon.
So it's more energy waste.
Energy waste is better. So so it means that energy, why we say waste better, because here we want all our electron to recombine through here, right? And then the energy loss will be in terms of photon. However, when you have defects like this, you have energy loss as well, but you will lose it in through a phonon. And why is it a waste? Because waste something that we don't want, right? So instead of all of your electron being recombining to give out phonon, some of your electron will recombine through defects, and you get phonon heat. So it means that it's not efficient. Your LED, your laser will not be efficient if you have recombination through defects. And this is the second one. Any question? 454 dah. OJ, I will explain next class. Any question up to here?
Yes, I'm sorry, but I still don't understand why defect can introduce the energy level in forbidden gap. Why? Like, can it introduce in same energy level as conduction band and valence band?
Yeah, but it doesn't, if it's in the conduction band or in the valence band, it doesn't matter because there are many energy level out there. The electron can sit anywhere. But because it's more significant if the energy level is introduced inside the band gap. You can have, if the traps introduces energy level in the conduction or in the valence band, no problem, because you have many other energy level there as well, so to occupy. But the problem is in the band gap, there's no energy level, so it disrupts the process of the semiconductor device if it's in the band gap. Does that answer your question?
Yes, but why in forbidden? Why, like, how the defect introduce energy? Like, it's
So
loss
it's
of
the,
atom, but how? Yeah.
so it's the same question as how last time we were talking about dopant. How does dopant introduce energy level inside the band gap? You didn't ask that question before, right?
No.
Yeah, it's the same thing.
Yeah.
It's the same thing. It's just is a, what do you call it, is a, somehow it's a hypothesis. This thing, this energy band diagram, nobody have seen this energy. It's just something that we introduce to make, to simplify how we explain how the semiconductor works. You understand?
Yes.
So if we put it there, when we put there, everything works. We can explain nicely. That's why it's there. If you don't put it there, we cannot explain how the semiconductor works. So it's like a hypothesis. So that's why science is not the real truth. People, it's not al-haq. It's something that human being introduce or think. We think, like this, and this explain this, why not we put the hypothesis like this, we put the theory like this. But in actual term, we don't know. But when we put it like that, we can explain certain things. You understand?
Yes, yes.
So this is just a way that makes the everything fall in place. Is we can explain many things by having this theory. But maybe one day it will be wrong. For example, previously we thought light is just a wave. Then that's a theory. Then after one time they do experiments, say, hey, it's actually a particle as well. Then they introduce another theory, particle wave duality, something like that, in order to explain. So it's similar like this as well. So it's just like you need to have faith, belief, plus some logic. We just understand it translate how it translates. Otherwise, we don't know how to explain why why LED doesn't have some of it shine a lot of light or some not, and how does that relate to the defects. So in order to answer that, we introduce this the defect introduce energy level inside the band gap. Okay.
Yes. Okay.
Any other question? No? Sorry, 5 o'clock. Maybe your head is burning, tired maybe of the whole day learning. So you can go and watch again. And if you have question, make sure you ask in the next class. Don't wait until many classes. You'll be in deep trouble. You need to understand. Make sure you, even the small thing, the difference between imperfection and impurity, things like that, right? If you are not sure, you ask. If you still confused a bit, you ask, because later on there are more things that you get confused with. All right, I think that's all for today. Hopefully you understand. If not, I will put the video in the YouTube. But there are many other my previous classes on YouTube. If you want to have a look, watch. Oh, my kaki dah cramp. Okay, so now let's end the class with doa, please. Okay. Any volunteer? No volunteer will stay here forever. That's how it.
Can I volunteer?
Okay, good. Silakan.
Bismillahirrahmanirrahim. Alhamdulillah alamin hamdan fina kafi mazida ya rabbana lakal hamdu Allahumma jannibna min at-tawabi wa ja'alni min taqibin wa ja'alni min ibadika salihin Allahumma wa ilayya wa Allahumma kama rabbayana shighara wa jumla isma al-muslimin wal mu'minat al-ahyam gama bi rahmatika ya arhamar rahimin rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina adzaban nar sallallahu alaihi wa Muhammad wa ala alihi wa sahbihi wasallam alhamdulillahi rabbil alamin.
When you make dua, don't close your mouth. We cannot hear you, you know. If I speak like this, can you, if I teach and I speak like this, you like me teaching like this? Or you like me to teach like this? Right? So it's so I'm just teaching you how to communicate with others. Sometimes interview, I think so people cannot hear you, and that's why they don't hire you, because you have this not you. I mean, I'm talking about other people. Then when they talk, they like to. I'm thinking, but you thinking, you close your mouth, so people cannot understand you. So and make dua like this, make sure your mouth are clear. All right, thank you, Brother Nasrin. Let's end with tasbih kifara and surah al-asr. Subhanakallahumma bihamdika nashhadu an la ilaha illa anta nastaghfiruka wa natubu ilaik. Bismillahirrahmanirrahim. Wal 'asr innal insana lafi khusr illa allazina amanu wa 'amilus solihat wa tawasaw bil haqq wa tawasaw bis sabr. I'm going to the beach after this. So